colleagues and all the viewers who are watching this program live from Facebook page and YouTube channel. I would like to welcome you all to our International Physics webinar. So, good evening to all here in Bangladesh, and a very good morning to all those who are watching this program live from USA. Today, I would like to welcome you all to our International Physics webinar. So, it's our 172nd International Physics webinar, and today, this is a joint session between Department of Physics, Pabna University of Science and Technology, and the Department of Physics and Astronomy, Iowa State University, USA. And we have with us here today Dr. Alex Travesset, sir, Professor, Department of Physics and Astronomy, Iowa State University, USA, and he has already connected with us. So I'd like to welcome our speaker, sir. Good morning and good evening to here. So thanks for accepting our invitation. And this will be a great opportunity for our students to learn a lot of things from you. And for those who are new, I'd like to inform you all that we have divided our webinar into three parts. First of all, I would like to introduce our speaker with all of you, and then our speaker will deliver his piece, and at the end we have a discussion session. In that time, anybody can join with us, and you can ask questions by commenting also. I think you have already come to know the title of this today's International Physics webinar, and title is the Programmable Assembly of Matter. And our speaker is Dr. Alex Travesset, sir, Professor, Department of Physics and Astronomy, Iowa State University, USA. And we can see some information from our professor. So Dr. Alex Travesset got his PhD from the University of Barcelona in 1997 after postdoc position in Syracuse University and University of Illinois at Urbana-Champaign. He joined the faculty of Department of Physics and Astronomy at Iowa State University, where he's now full professor. He also holds an appointment as an associate scientist at the Ames lab. You can see his ResearchGate ID. His ResearchGate point is 40.34, and this is his Google Scholar ID. His citation is more than 5,779, and this is recent publication. So thanks for all of your patience. Now it's time to go to our speaker. So sir, thanks again for giving us this opportunity to arrange such an important webinar. And it's your time, sir. You can start your session.
Okay, thank you very much for this nice presentation. So I'm Alex Travesset, and the title of my talk is Programmable Assembly of Matter. I would like to mention that I'm giving the talk from US. We are very far. Also, I cannot see the audience or anyone else, so please feel free to interrupt me if you have any questions. And then at the end of the talk, we will have some time for discussion. But I mean, if there are clarifications that you need or some things that you would like better explained, I'm more than happy. I have a lot of stuff to talk. I mean, I will just move from one topic to another at some point. But I'll try to make it so that people can understand. So first, let me introduce, those are the graduate students that are currently in my group. Some of them graduated soon. Undergraduates, we also have many of those. And we have experimental collaborations here, mostly at the Ames lab. And I also have some external collaborators. Mostly in theory, I have Hongxia and Xianxie from the Chinese Academy and Carlos Calero from the University of Barcelona. And in experiment, those are experiments that I will discuss a lot. I would like to mention Dimitri Talapin and Michael Bowles at the University of Chicago and Stanford, Oleg Gang at Columbia, and Eric Garnett and Biplab Patra at AMOLV, and Maxim Kovalenko in ETH Zurich. I would also like to mention that I am the editor of Computational Material Science, and we are always looking for good papers that you would like to submit to our journal. I'm just doing some advertisement. Okay, so I would like to start with a quick or not so quick introduction about what is the type of research that we do. And the main thing is thermodynamics. And for those of you, I'm sure that you have some knowledge of thermodynamics. The basic function is the free energy. And this is a balance between the actual energy, the internal energy of the system, and the entropy. So that a physical system finds equilibrium, finds that state where the properties of the system do not change by minimizing this function, which is the internal energy and the entropy. Now, typically, in many places at least, I mean, the energy is seen as like the ordered principle where everything is good and in harmony. And entropy is kind of this disorder, this bad thing that tends to do bad things to systems that do not find nice ordered structures. I want to say that this is actually a very incorrect view of thinking about physics. In what we do, entropy plays a fundamental role. And entropy not only is a fundamental role, entropy is a source for order. Yeah. So, I mean, this idea of energy order, entropy disorder, when you do the type of studies that we do and the type of systems that we look at, it's actually not what happens. In fact, for example, I mean, there are many cases where entropy leads to order. I mean, for example, in liquid crystals, that is this type of molecule, which is very rigid. It's almost like a rigid rod. If you put many of these molecules, they form a liquid. But this liquid is not actually a normal liquid. It's a liquid that has some order, that it is called nematic, and it's everything due to the role of the entropy. So those are the main principles. I mean, nature finds equilibrium by a balance between energy and entropy, and we shouldn't be looking at entropy as being the bad guy. Actually, entropy helps. I mean, you will see many examples where entropy leads to order. Now, there are many different elements that we use. We use polymers. For those of you that are not familiar, a polymer is just a molecule that consists of repeating structural units, typically connected by covalent chemical bonds. So, for example, DNA is a polymer. You can see it here, how it's basically a chain. Here is a closed loop of DNA that you can see. Proteins are also polymers. You can see that they start at a point here, and then there is a sequence that goes this way, and so on. Proteins have a lot of structure, but they are still a polymer. They have a beginning, they have an end, and then in between, they are basically repeating units. Yeah. Another polymer is Pluralic Polymers. That it's a polymer that we've studied a lot. Those have this particular form with polyethylene oxide and polypropylene oxide. And what is the property that these polymers have is that there is this part here, which is mildly soluble in water, and then there is this part which is insoluble in water. So when you put these together, you have a situation where the polymer wants to be both soluble and insoluble in water, and that gives rise to all sorts of structures. Another element that we will be describing are nanoparticles. Those are the most important elements in our discussion. So what is a nanoparticle? So a nanoparticle is a combination of a small number of atoms. So here you have an example of a nanoparticle. The gold are gold atoms, and the red are sulfurs. And we will discuss why this is relevant. So basically what you have here is that you have a material, but instead of being a material like a big material, like the one you see with your own eyes, these are very, very tiny materials. They are about the nanometer, in the nanometer scale. They contain 3,000, 5,000, maybe 10,000 or 100,000 atoms. You know that in general, a normal material would contain an Avogadro number, which is 610 to the 10 to the 23. So those are the smallest possible materials that still display properties of materials. Because if you take one atom, well, one atom doesn't really conduct electricity, doesn't conduct heat, doesn't do all these things that materials do. Yeah, I mean, a single atom doesn't have bands, for example, which is fundamental in order to conduct electricity. So the idea is that how smaller you can go by dividing an actual material to make it that you still have the properties of a material? And the answer is the nanoparticles. So the nanoparticles is something that looks like this, and in general what people do with nanoparticles is that this is what will be a bare nanoparticle, but then what you do is you functionalize them. That is, you stick other molecules to these red things, the sulfurs, and then you have a combined system which consists of a core, which is this part here, and then you have a shell, which is these molecules that are grafted to the nanoparticle. And this is what a nanoparticle looks like. Here you have the full system, which consists of the core, which you can barely see, and then the grafted molecules that are Okay, should I go again?
Connected.
Sorry
Yes,
about
we hear.
that. I mean, I don't know what's happening. I
Sir,
mean, I mean, usually the internet works pretty well. I don't know what is going on here. Okay, should I go again?
yeah. If you can start sharing.
Okay. So, sorry. Where did I stop, by the way?
Maybe the previous page. Could you go the previous page?
These nanoparticles?
No, no, could you go the previous page? You,
This one
no, no, previous one.
here, polymer?
Yeah.
Okay. So a polymer is, as I said, is repeating units. And here we have proteins are an example of polymers. And pluronic polymers are other types of polymers. And and then the next element that we want to discuss is nanoparticles. Nanoparticles are the smallest materials that still have the properties of materials. So, for example, if you have one atom, then typically, an atom doesn't conduct electricity, doesn't conduct heat. So you need to have a minimum number of atoms before you can have a material. And this is actually what a nanoparticle is: the smallest type of atoms that you have where you can behave as a material. And this is an example of a nanoparticle that we use in our molecular dynamics simulations that I will talk later. And you can see here that those are gold atoms, but gold is not the only way. I mean, there are cadmium selenide, there are many other types of nanoparticles, there are a huge number of nanoparticles. And typically, these nanoparticles we functionalize with inorganic organic molecules like this one, so that they are attached to the nanoparticle. And what an actual nanoparticle looks like, the combination of both this part, which is the core, and the ligand, is something that looks like this. Here you have it. Here you can barely see the core because everything is grafted with this. In this case, a hydrocarbon. This is an example of a very short polymer, but you can have many other molecules that you functionalize. So why do we need to functionalize? Well, the reason why we need to functionalize, the reason why we need to attach these molecules to the surface of the nanoparticle is because if you put this particular one, like gold, in a solution, these will precipitate. They will appear at the bottom and nothing interesting will happen. So in order to make these nanoparticles stable in a solution, in this particular case, you want them to be stable, for example, in an organic solvent like toluene, you need to functionalize. And there are interesting properties that happen. So here you have, for example, nanoparticles which have different sizes. Those are the smallest one, those are the largest one. Then you shine electromagnetic radiation. That what this does is that it promotes an electron in the conduction band, in the valence band to the conduction band, and leaves a hole behind. Eventually, this electron-hole pair recombinate, and when they recombinate, they leave out a photon. And you can see that the color of the photon, that is the wavelength of the photon, depends on the size of the nanoparticle. So even though those are materials, they are materials that depend on the size. Yeah. So you see that as they become larger and larger, the electromagnetic radiation becomes of higher wavelength. Okay. So this is actually one of the examples of the many properties that nanoparticles have. So in typical materials, the size doesn't matter. It doesn't matter if you have a material which has the size of the Avogadro number of 3 times the Avogadro number of 10 times the Avogadro number. But when you go to these small systems, there is also a dependence on what is the size that reflects in these properties. This allows them to be very important in terms of identifying different applications like spectroscopic studies and many other things. One goal of the nanoparticle system is to put many nanoparticles together. So here is a solution where the nanoparticles are happily living here in this solvent. But what we would like to do is just to put a lot of nanoparticles together and then start having properties of these super solids or superlattices. So the idea would be that instead of having just one nanoparticle or many nanoparticles in a solution, you make a crystal that is an ordered arrangement of nanoparticles where they are next to each other, and they form a crystal which is made of nanoparticles, which itself is already a crystal. So what you have is a super crystal or a superlattice, which is what we describe here. And this is an example to show that a nanoparticle has um, energy levels, and as you put them together by quantum effects, you know that they will end up developing some band structure, and the goal would be to have a superlattice, which is actually an electric conductor, where you will have that. And this is actually something that it is called the mode transition, but we are not going to investigate at this point any further. Okay, so Kumar, I would like to appreciate if from time to time you say something to make sure that I'm not disconnected.
No,
Are
it's
you
okay.
there?
No, 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 no. We can hear you and see the
Okay.
slide also.
Are there any
So
questions
everything
so
is okay.
far? So let me just summarize where we are. Yeah. So we have this physical principle, which is the free energy. This is the minimum of the free energy. It's the balance between internal energy and entropy. And then we are going to apply this fundamental principle that applies to everything, to these systems which consist of nanoparticles that are grafted with these organic molecules that can be polymers, that are the ligands. And what we would like to do is to see how we can put together all these nanoparticles to make actual crystals. And that has been achieved. So the idea is that we have now at our disposition a new periodic table. So we know that the periodic table is built by nuclei that are protons and neutrons. Then to this nuclei you have electrons, and that makes an atom. Then these atoms can do, through bonding, can form other molecules. This would be an example of a covalent bonding. And then out of these molecules you make materials. This is an example of a material that it is actually graphene. Okay, graphite. Okay, so you can see here, then you form these new materials, which are typically crystals. I mean, meaning that the material consists of this unit that it is repeating over and over and over. So this is how you traditionally make materials, and this is your periodic table. You choose from here several elements. You have your atoms. You do covalent bonding, and then you make material. Now this suggests a new strategy to make materials, where you start from one core, nanoparticle core. And this nanoparticle core, instead of being determined by the number of protons and neutrons, is determined by the size. I mean, how many atoms you have, the shape. We can change the shape. We can change the composition. I mean, we can, instead of having gold, we can have cadmium selenide, or we can have many others, or lead sulfide, and many others. And here's an inventory of, actually quite old, of all the nanoparticles that you can have. Yeah, I mean, you can have in different shapes, sizes, etc. So this would play the role of the nuclei. Now, you can go and functionalize, graft to these nanoparticles, all of these nanoparticles with different molecules. And these together would form what would be the nuclei, and the electron would be played by these molecules. And then you would have an atom, which would be the core and the ligands that are here. And then the next step would be to make bonding. Yeah, so the idea would be how to bond two of these functionalized nanoparticles, or nanoparticles for short. And then the next step is, when you have achieved bonding, how to make them into materials. And here's an example where I had to erase a little bit the ligands, because otherwise you won't see anything. But here you see how you can make these nanoparticles to make actually the same as we did here, a crystal. Now the question is that now we have at our disposition a completely gigantic periodic table, because now we have this shape, we have this size, we have the chemical composition. Then we can also functionalize with alkyl thiolated ligands, oleic acid, polystyrene, also DNA, and many things. Then we have this atom, and then we can make
dear viewers and students. We are very sorry that we have disconnected again. So we have lost our connection with our speaker again. So we're trying to reconnect. So please stay with.
Okay, sorry about that. I changed my computer because I was doing it from
Yeah,
my small laptop. I think now it will work better. I truly apologize. I
no,
don't.
no, it's okay, sir. It's okay. You can.
I mean, it shouldn't be happening, but I hope that I'm not losing the audience here.
No, no.
I really apologize. I'm really sorry for this. One second. I'm going to, as I say, I moved the talk to another computer that I mean, which is I think way more reliable. Again, I mean, I don't know why this is happening. Okay, so let me just go 1 second here. Let's see, 1 second. I don't know what is going on now. Sorry about that. I truly apologize. I mean,
It's okay.
so where did I stop?
Sorry. Can you
Where
hear me?
where was the last time that you now
Okay. Could you share your file? I haven't seen.
Pretam, are you there? Can you hear me? I don't see you.
sorry, 1 second, because now I'm having trouble with I don't know what is going on today. Well, okay, so let's hope that this will do it. I truly apologize for this situation. Okay, here it is. Okay. Okay, so I'm going to, do you see the talk now?
Not yet. Could you?
We
Is
have to
this
share. Yeah, 1 second.
yeah, sure.
Okay, so now is good. Yeah.
Yeah. It's better.
When was the last time I stopped?
Okay, could you change the slide so that I can next
Here.
slide? Yeah, now yeah, here.
Okay. So basically, what I said is that we have. I hope that I have truly apologize to the audience because I don't know what is going on, but it should be okay now. I mean, I changed to a computer, another computer. So what I said is that we have now. There is a periodic table that traditionally works by having a nuclei, adding an electron. Then you have an atom. These atoms bond each other, and then this eventually makes a material. In this particular case, is a crystal where you have repeating units. Okay, this is what we discussed. Now, what we have now is at our disposition is a new periodic table where we have here core nanocrystal. Then this core nanocrystal can be functionalized, and this core nanocrystal plays the role of the nuclei. It can be functionalized with the oleic acid or with any other type of system, also polystyrene, or we can have DNA and so on. And this combination makes what we would call an atom. This atom is obviously very different from the atoms that we study in traditional physics because, I mean, here it is, we have way more degrees of freedom. We have the composition, the size, the shape, and we also have the freedom to choose what type of electrons we want, that is what type of molecule we want to functionalize. Then that defines bonding. And then from bonding, you can also make the same way that we do with crystals. And these crystals are different because these crystals are crystals of crystals. This itself is already a crystal. So you are making a crystal which is itself made of tiny crystals. And now what we have to define is what bonding, what materials, and how this works. So we learned in basic physics that there are 3 types of bonding. And the same is true for, well, actually there are many more with when you have these new type of elements. So you have here that you could have ligand overlap, that is the 2 ligands, they overlap each other and they form these things, this bonding. You can have also what would be a polar equivalent bond by using DNA, where there are these parts which are complementary to each other, and you can even have a ionic bond. Okay, so this is an example where we show what crystals can you form. So this is an example where you have 2 different types of nanoparticles, and then you can see that they form these many structures that here you see with electron micrographs, and you see that they form all these different superlatives. You see that there is a huge number of different superlatives that you get by combining these 2 nanoparticles together. In the same way that you would combine atoms to form, for example, a diamond lattice. You can also form something that it is called a quasi-crystal, but we don't have to go there right now. It means some that have repeating units that do not conform to the usual symmetries of a normal lattice. So what is the goal of our research? Well, in our goals of research is that you have all these many elements like the nanoparticles, the ligands, and so on. And if you just let them in solution and do whatever you want to do, change the temperature of the solution, evaporate the solution, many things, if you just do it randomly, what you will get is just a mess. All these particles here will just form this mess. What you would like to do is just to have a way to define the interaction in such a way that when you put these things in solution, what you do is you form some ordered structure, for example, a nano-Taj Mahal. So that would be an example where you put these things together, and then because you cleverly define how these things interact, when they get together, they form a nano-Taj Mahal. And this is what will be successful self-assembly. So what we would like is to program the elements in such a way that they form interesting structures. But not only that, we would like to go even further. What does it mean going further? It means understanding how KBTs work. KBT is the basic unit of energy created by thermal fluctuations. And instead of building just one Taj Mahal, we want to build an entire city. And what is an entire city? An entire city would be, for example, a material where you have a semiconductor nanoparticle. Then you put a conductor nanoparticle that can conduct through tunneling, for example. Then an insulator nanoparticle, another conductor nanoparticle, and basically have a material where you can define what function you want and program the nanoparticles to do this function accordingly. And this is actually the goal of our research. This is what we do. We try to make sure how to define nanoparticles that form materials that are new in terms of structure or that they have new functions. So our goal is a theoretical design of nanocrystal materials, phases, or structure by programming the ligands. So the whole point here is that the combination of the nanoparticle and the ligands is what drives the formation of these new materials. So the idea is that if we are able to control the ligands and understand the ligands, we can predict and we can also form in the laboratory all these new materials. So this is what we do, okay? And this is something we've been working for a long time. It started with systems where you have nanocrystals that are functionalized with DNA, and then through pair interactions, they form structures. And this is actually an experiment that was done simultaneously by these groups, and this is something we've worked a lot in the past. Then there are these other systems that I already mentioned where they are functionalized with hydrocarbons. And here we worked a lot. Here we have all our recent work. Then there is some other work that we've done with in collaboration with our experimental colleagues, where we have non-ionic polymers in water, and we change the ionic strength, and we are able to form many new materials, or working with diethyl linkers. And also, more recently, which is kind of a continuation of the hydrocarbon organic, we've been interested. Oh, and there is also interpolymer complexation, also in collaboration with the Ames lab, which is similar to DNA, except that instead of using DNA, we use these things that they form hydrogen bonds. More recently, we were interested in perovskites. So those are fascinating new types of nanoparticles that are cubes. Those are the blue cubes, and we combine them with spherical particles. And this is actually a timely talk because, I mean, there is a recent paper that appeared in Nature just today, and this is the cover letter. This is exactly the paper that I've been involved. We just published in Nature today, so this is actually as fresh as it can be, where you can see here that those are the cubic nanocrystals, and those are the spherical nanoparticles. And they form new materials that have fascinating properties that I hope I will have some time to talk about it. So those are basically everything we do, and our group does computational and theoretical work. So we don't do experiments, but we collaborate with a lot of experimentalists. I mean, here we have Maxim Kovalenko at Zurich. Here we have Oleg Gang at Columbia University in New York. Here we have our colleagues at the Ames lab here, and here we have the work with Dmitry Talapin at the University of Chicago. So this is actually gives you an idea of the whole diversity and incredible variations that you have to make these materials. And I will hopefully describe you a little bit. I mean, unfortunately, because of all this back and forth with the problems with the connection, we've lost valuable time, but I hope I can walk you at least to some part of it. So let me just concentrate on these types of parts. I will not be mentioning these. If you are interested, I'm more than happy to discuss them in the questions section, or if you are even more interested, you can send me emails and we can have a longer conversation. So binary superlattices consist of two types of nanoparticles, which have different sizes. And this, the color means the core, and the gray means the ligands. Yeah, so we have nanoparticle A, nanoparticle B. Those are capping ligands, the hydrocarbons. We put them in a solvent, something like that. And then what you do is you evaporate the solvent in some controlled way. And what you are left with is these nanoparticles. So after you evaporate the red part, which has the nanoparticles inside, when you evaporate the red part, what you are left with is this system. So our work is to model this system and predict what happens. So how do you model these systems? There are different ways to do it. Here they are not polymers, so you cannot use the very dense literature on polymers. There are these parameters that I'm not going to go in a lot of detail, but the first step would consider these systems to be hard spheres. So first approximation, and as a physicist, that's what you always do. You just say, okay, let me go with the easiest and most clear or more straightforward approximation that hopefully still captures the properties of the system. So first one would be to just make this whole thing to look like a billiard ball. Yeah. You will say, oh, wait a moment, but you shouldn't do this because these ligands here are flexible, so therefore this is not a billiard ball. I mean, this should be something that has some flexibility. Well, we'll get there. But right now, let's try to see what happens when you go with the straightmost approximation, which makes that a billiard ball. Oh, then becomes a packing problem. So this is what we have here. You know, packing when you have to travel, you don't travel very much these days because of the pandemic, but you know, we used to do these things, and then the idea is to pack things. Yeah. So what is packing? So for example, if you have coins, two-dimensional systems, you could pack them in a square lattice, and then that will have a fraction of the lattice of the space that it is occupied, and then another one which is not occupied, or you have the total space. What is the fraction of space that is occupied with respect to the total volume? Well, the total area is 2r, where r is the radius of the circle, and the occupied area is only pi r squared. So in this particular case, the packing fraction is pi over 4, which is 78. So this means that 78% or 78.5% is actually occupied, and the rest is free space. Yeah. In 3D, you can do the same thing. The packing fraction, there are the FCC, BCC, simple cubic, and you see that FCC is the most efficient way to pack equal spheres. In binary systems, you can improve. Yeah, in binary systems, you can go with packing fractions that are even larger than these ones, because the idea is that when you have this for example, two-dimensional case, then you can pack with here with the additional interstitials with additional circles, and these circles, you know, occupy some additional part. And now what you see is that now the packing fraction here is just a number. Here it is a function of the ratio between the radius of this particle and the radius of the other one. So in other words, we define a parameter gamma, which is the ratio of the smallest to the largest nanoparticle. And in general, the packing fraction will be pi4 plus some function of gamma, okay, some function of gamma that you will have here. So now when you go to 3 dimensions, instead of getting just one packing fraction, what we will get is a function that depends on what is the ratio between the two spheres. And this is what it looks like. So those are different lattices, and you see that these different lattices have properties in the sense that they have typically a maximum of the packing fraction that happens for different values of gamma, which is the ratio of these two numbers. So when we do this thing, and then when we do an experiment, we can assign a radius to this, and then we can plot this, and what you see here is that the experiments typically happen around the maximum of the packing fraction. So what we see here is that the billiard balls is actually a good approximation. It's a good thing. It predicts something, but it is not quite there yet. Because, for example, you have here that this is good, but then you also have others that happen at very low packing fraction. And that is something that we need to understand. So you see here that they are close to the maximum, but you also have some that happen at very low packing fraction, and this is unphysical. So the first step of modeling this as billiard balls is successful, but only partially so. There are many things that cannot be explained. Also, the other thing that you see is that this maximum of the packing fraction happens below the line of the FCC. So in other words, this system in principle would be more efficient by packing two single component systems as opposed to two. Another step is, okay, let's say that we can make, instead of billiard balls, we make them into tennis balls, which are flexible. Yeah, so the idea is that, okay, maybe that will improve. Well, I mean, that's what it is. So instead of having a potential that it is a rigid, we let some particles to overlap. And let's say that we've done this, and the answer is that it doesn't help that much. I mean, it's not possible to explain the experiments only with this. Okay, so what is next? Well, the next is to consider the ligands explicitly, and I'm not going to go because I don't have much detail, but basically we developed a new theory where we have to consider the flexibility of the ligands and some topological considerations that have to do with topological defects and so on. But the important thing is that we are able to get a model, a new model, the OTM model, we call it, that is able to predict what will happen. So let me show you. So basically, the idea here is that under some circumstances, which we are able to understand very well, the tennis ball is not a good description, and what you have to have is these soccer balls that are deflated. So how this deflation happens is part of the theory. I'm not going to go into detail, but basically the idea is that it is not just enough to have this flexibility. You have to have this deflation that happens. So I'm going to skip that part. This explains how the deflation happens, the presence of vortices, but the bottom line is this. For example, here we see that we have all this low packing fraction. When you take into account the deflection, what you see is that this branch here, which has low packing, is substituted by this high packing fraction, and now everything is in agreement with experiment. So let me show you this result. So this is actually the hard sphere prediction. This is what the experiment is. This is the packing fraction. This is the packing fraction measured in the experiment. This is the packing fraction that it is from hard spheres. And then when you take our model, which has no fitting parameters, we get all these things. And there is here an outlier which actually can be explained. That was a very successful prediction that we were able to with the experiment. And for example, here's what the packing fraction looks like. This is the hard sphere packing fraction. You see that it is very far off from the experiment. When you take into account the OTM theory, this line gets converted into this other line, and everything now is in agreement. Okay, so now what we've been able to understand is how the bonding occurs, and the bonding in these nanoparticles occurs in a way that it is actually quite interesting. It behaves like billiard balls, but then in some circumstances that I have not described, but you can find in my papers, and I'll be able to describe it in more detail if you want more questions, we're able to tell that there will be these situations where they completely deflate, and that increases the packing fraction and brings it in agreement with parity. Now we can use this knowledge to make more predictions and predict other types of lattices. I mean, there is also a connection with higher dimensional spaces that I'm not going to go into detail because I don't have time, but basically that is the so-called Frank-Casper phases. In the time that I have left, which is not much, I mean, I would like to mention, that we also do numerical simulations. Over time, we've developed many tools to do types of simulations. We have calculations of free energy and this from DLT. And we also have developed many years ago, I mean, 10 years, actually 12 years, 13 years ago, this code with my former student, Anderson, which actually was the first code that allowed to do molecular dynamics on GPUs, on graphic processing units. That is the type of things that you use to play video games. So we have developed a lot of tools to do this type of calculations. This is a general program that it is freely available and it is used by many people around the world. And we've done simulations. I'm going to just mention that we were able to see the deflation. Here you have it, the deflation that I was mentioning, which is called vortices. And we are able to predict basically all these things and confirm the validity of the OTM theory that we very much described. We have excellent agreement with experiment and so the use of numerical simulations allows us to show all these results. Here we have calculations of free energy, which shows that indeed the structures are the minimum of the free energy. Here you can see the blue line is the minimum of the free energy, as I was mentioning in the introduction of my talk. And in the last 5 minutes I have left, unfortunately, this has gone very quickly. I'm going to skip that. I'm going to talk about the perovskites, which is this paper that we just published in Nature precisely today. This is some situation about, so perovskite nanocrystals, here I have it. So those are cubes, as I mentioned. They have the form cesium, lead, and some X. Typically, they are halide perovskites. Most common is bromide, but could be anything else. This is our first paper. And then what we did is we studied what is the structure of the ligands. That is, this is the core. And now we have to functionalize. There are two types of ligands that we looked at. And here you see how, I mean, an example of the structure they make. But the important thing is that our simulations show that these cubes, remember that in some situations they become floppy. and they become floppy around the corners, as we see here. So this is what we have. So if you have sufficiently large, they become like hard cubes, except at the corners. So perovskite cubes form vortices at the corners, even at high density. And one important success was when this group here, which I collaborate with them, I mean, like 3 years ago, they were able to make cubes by solvent evaporation. So they put the cubes here, here you have the solvent, they evaporated the solvent, and they found what you can see here, these huge superlattices which have cubic structure. You can see here that when you magnify this corner, you can still see the single cubes that are formed there. And one thing that happened is that, surprisingly, these materials exhibit a property which is called superfluorescence. So here you have the evidence. So what you see is you shine electromagnetic radiation, and what you see is that instead of re-emitting the electromagnetic radiation typically, as you hear, they do it as a single pulse. So basically what happened is that you excite the material, then all the different dipoles, the emission dipoles start aligning each other, and when they are aligned, boom, they emit a huge burst, which has a lot of power, and it is very precise in terms of the wavelength. So this is actually an example that shows how the structure determines the function. This function here is this effect, which is called superfluorescence. So in our recent paper, the one that appeared in Nature today, what we did is we just combined spherical nanoparticles with cubes. And how to do that? Well, you just do it and it happens. So we have here two structures, AbO3 and sodium chlorine. You can see here that the cubes are ordered in different ways. They are oriented in different ways. Here you see this is actually a simple cubic lattice of spherical particles. And then you have cubes that are oriented in the different way. And here the sodium chlorine. And what is interesting is that this one has superfluorescence, but this one does not. So superfluorescence remains only for aluminum boron, AbO3, but not for this one, showing that the structure has a fundamental role in determining the superfluorescence properties. So anyway, I don't have more time. I try to stop on time. I just will make some conclusions. I've talked about programmable matter. This is only one aspect. I mean, this is only one system that we've considered. And I showed you how you start with a model, which is billiard balls. Then you realize that that model is not suitable. You go to balls that are more deformable. You realize that that doesn't explain it. And then you have this situation where under some circumstances, you can deflate the balls. And that is what successfully explains these structures. So sometimes behave like hard spheres, sometimes flexible, sometimes vortices. What it is true is that they are always described by this model that we introduced, the OTM model. And this is actually what explained. The soft, I mean, I haven't talked about that. I try to avoid more technical language, but those behave as orbitals. Here you have, there are strong tendency toward the icosahedral order, something I haven't described, but there is an intricate structure that reflects topological and geometrical connections that, I've been mentioning around. And there are new fascinating perovskite materials that we just had started looking into that, and all of them are becoming, they are having incredible new properties that we will be working more in the near future. So basically, we are trying to design things. I haven't described many other aspects that we have done to design new structures, but the principles are that they form high packing fraction and tetrahedral or icosahedral order. And I would like to conclude by saying that whether driven by DNA, polymers, or hydrocarbons, nanoparticle assemblies are an extremely designable new form of soft matter. And with that, I will stop here.
Thank you, sir, for your wonderful presentation. So if you allow, we can start our discussion session. We have got few questions.
So I want to apologize again for all these.
It's okay.
I'm really sorry, but sometimes happen. Yeah, fortunately, we were able
this is
the second part of the talk without any other thing. So I would like to enjoy any questions. Also, I would like to mention that.
So okay, so you got a few questions. The first one: what are the binary superlatives?
Sorry.
What are the binary superlatives?
What about?
Okay, I can send in the chat box so that you can maybe
Yeah.
there is
Let
a
me just mention that I would like to mention that at Iowa State, we are always interested in having new interested students. So if any of the people in the audience is interested in applying, just
yeah,
go
of
ahead
course.
and apply or let me know. Yeah.
Okay, of
If
course,
you are
of course.
interested to do graduate school at Iowa
Yeah,
State or
yeah.
even in my group. Yes.
Okay, so then what are the procedure for applying in your group?
I mean, the only reason is that you go to the Iowa State Physics Department, and then you just follow the procedure. And also, I mean, if you are accepted, you will be provided with. All of the students are provided with the scholarship that will allow them to live at Iowa and so on, meaning that you will be covered. Yeah, it will be
Okay.
supported, fully supported. If you are accepted, you are fully supported for the 5 years that you will do your PhD. Okay.
Oh, great.
Okay. So here, what are binary superlattices? Okay, well, binary superlattices. Let me just see. It's just a system. Let me show you um, an example. So do you see the screen?
Yeah,
So
I can.
binary superlattices are superlattices that is ordered nanoparticles of two types of nanoparticles. Okay, that is why it's called binary. So here we have an example: sodium chlorine, copper, gold copper. We have aluminum boron 2. So basically, what you have here is that you have a lattice in the unit cell. You have two types of nanoparticles. This is a binary superlattice, and this is something that we've studied a lot. Actually, our perovskite system is actually a binary superlattices. We have also ternary superlattices. Here you have it. You can see, wait, here. So you see here that there are two types of nanoparticles. One is spherical, the other is a cube, and this is what it looks like in an electron micrography. Okay, so I hear. What is superfluorescence? How can we combine perovskites and spherical nanoparticles? Well, I mean, that is the exact situation. This is how you combine, this is what it looks like. So the superlattice in this particular case is periodic repetitions of this motif. Yeah, so you imagine that you have these spherical nanoparticles, you have these cubes. Those have been obtained by solvent evaporation. I have not been very detailed about it. And then this repeats all the way and forms uh, that material. Yeah, aluminum boron 3. The sodium chlorine is one where the cubes are aligned along the lattice units. In the BO3, they are rotated. So this is a binary superlattice with perovskites. Let me see the question. And then what is superfluorescence? Well, here's what is superfluorescence. Yeah, so superfluorescence is better explained with this transparency. So what you have here is this: you have already assembled this system. This is a cube superlattice, a superlattice with cubic structure. Then you shine electromagnetic radiation, and then typically, if the system doesn't have any order, this will be re-emitted somehow or somewhere. Here, what happens is something different. What happens is that the electromagnetic radiation, what it does is absorbed by the system, but it is not re-emitted. Then the system starts. You have dipoles in all these different. So these dipole, instead of radiate each one separately, they all align, and then at some point they emit a burst of radiation where they emit the entire radiation all at once. And this is a very coherent source that includes many. Typically, we've calculated around 20 or 30, but it could be more. And you can see here that it is very sharp. It has a very precise wavelength. Okay. So this is what superfluorescence is. Yeah, so that's yes, that's answered the question. Yeah.
Thank you, sir, for your wonderful presentation and discussion session, sir. So, as we don't have any more questions, so we should conclude our discussion session, sir. So it is a very great webinar with you, and this is a very good opportunity for a student to learn a lot of things about nanotechnology. And you have already mentioned that if anybody want to join your group, they may apply for it. So thanks for everything, and uh, thanks for giving us opportunity to attend such an important webinar with you. So I
Okay.
hope.
Well, thanks for having me, and I'll be happy to answer any other questions that may come through email. Okay.
Yeah, of course, sir. So
I'm
as
going
the
to log off.
stay remain in YouTube and Facebook. If anybody will ask question, they might write there, or they might send you the email about the
Okay,
question.
that's great.
Yeah, thanks
Okay,
again, and have a nice
okay.
day.
Thank
Bye
you. Bye. Good night.
bye.